Welcome back. Problem 6-75. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by Rc Hibbeler. So statement is the shaft is supported by smooth thrust bearing at A and smooth general bearing at D. If the shaft has cross section shown, you can see the shaft cross section. The outer radius is 40 millimeter and inner radius is 25 millimeter. Determine the absolute maximum bending stress in the shaft. So this is the shaft. At A we have a smooth general thrust bearing. At D we have smooth general bearing. At B and C we have a 3 kilonewton load that is downward. The length is shown over here. The total length is 3 meter. Clear? So you have to find the absolute maximum bending stress in the shaft. So let's start with the solution. So first step is that if you remove this smooth thrust bearing, so you will be having reaction force exerted by this bearing on the shaft, which is equal to Ra. And if you remove this smooth general bearing at D, so it will apply a reaction force Rd on the shaft. So we'll find this Ra and Rd by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0 and taking the counterclockwise movement as positive. So about point A, the first moment will be this 3 kilonewton load and perpendicular distance is 0.75. It is clockwise, so it will be negative. So I will write minus 3 into 0.75. The second moment will be due to this 3 kilonewton load, and now perpendicular distance is this one, which is 0.75 plus 1.5, and that is 2.25, and it is also clockwise, so it will be negative. So I will write minus 3 into 2.25 meter. And the last moment that is produced due to this Rd and perpendicular distance is this total is 3, and this is producing clockwise, counterclockwise, so it will be positive, plus Rd into 3. And the sum of all this moment about point A must be equal to 0. So when you calculate it, you will get this 3 Rd will be equal to 9, and from here you will get this Rd will be equal to 3 kilonewton. Okay, now you have this Rd, so you can find this Ra by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So Ra, which is upward, so Ra minus this 3 kilonewton and minus this 3, so minus 3 plus Rd, which is plus 3, is equal to 0. So from here this will cancel with this, so Ra will also equal to 3 kilonewton. Now you have Ra and Rb, so we will move toward finding the shear force and bending moment diagram, because we have to find the maximum bending moment and maximum bending stress, and that maximum bending stress is maximum bending moment into C divided by I. So here the hollow circular shaft, so it will be outer radius. So for finding a maximum bending moment, we will draw the shear force and bending moment diagram. So again, for that I will take the vertical line from the end of this beam, clear, and then horizontal line to show the length in x in meter. On y-axis we will have shear force that will having unit kilonewton. Let each division is 1.5 kilonewton, so this is 3. Similarly minus 1.5, you can choose as per your required scale or chosen scale. Now you can see that first at Ra we have, at point A we have Ra, which is 3 kilonewton. So your first point will be this one. Now moving from point A till point B, there is no other shear force. So till this point B, this shear force will remain horizontal. Okay. Now at this point B, we have minus 3, that is downward. So plus 3 minus 3 will bring it to 0. So shear force will change from 3 to 0. Now again from B to C, there is no other shear force, so it will remain similar horizontal line till point C. So this is your point C, this is your point B, this is C. So this shear force remain horizontal. Again at point C you have minus 3 downward, so 0 minus 3 will be equal to minus 3. So shear force will change it here, and it will be minus 3. And moving from C to D, there is no other shear force, so it will remain same horizontal line, clear. And at the end you can see you have Rd, which is plus 3, so minus 3 plus 3 will bring it to 0. Okay, so this is your shear force diagram, SFD, shear force diagram. Now we'll find the bending moment diagram. For that I will draw horizontal line again to show the length of beam, and this length will be in meter. And on y-axis you have moment that will have unit kilonewton into meter. So let one division is 1 kilonewton into meter. This is 2, this is 3. Similarly minus 1 minus 2. So at x is equal to 0, we have moment is equal to 0. Now the first area under the shear force diagram is this area, and this area is this height, which is 3, and this length is 0.75. So 3 into 0.75 will be equal to 2.25. So at this point we will have 2.75. So first we will locate 2.25, sorry. So let this point is 2.25. Now you can see that shear force is a horizontal line with this area is positive, and this is 0 degree line. So bending moment will be 1 degree higher. It will be a linear line, and slope will be increasing. So you will join these 2 points using straight line. Now here in this region there is shear force is 0, so bending moment will remain constant till this point. So it will be a straight line till this point. This will be 2.25. Now the area under the shear, this area under this shear force diagram is minus 3 into 0.75, which is equal to minus 2.25. So plus 2.25 minus 2.25 will bring it to 0 at this point. Clear? So your new point, bending moment at this point will be 0. And you can see that shear force is a horizontal line with this area is negative, so bending moment will be a linear line and slope will be decreasing. So we'll join these 2 points using a straight line, and that will be your BMD, bending moment diagram. Okay, now from BMD, bending moment diagram, you have bending moment, maximum absolute value of bending moment is equal to 2.25, and unit will be kilonewton into meter. Clear? So this will be the maximum bending moment, will be 2.25 kilonewton into meter. So we have been given the hollow circular shaft, outer and inner radius are given, that is outer is 0.04 and inner is 0.025 meter. So I for circular second moment of inertia of circular shaft is pi by 4 into c outer power 4 minus c inner power 4, where c is the radius. So you can just put the value pi by 4, c outer was 0.04 power 4 minus c inner is 0.025 power 4. Clear? And what about c outer? C outer is the maximum distance from the neutral axis. So you can have all, now you have all the values, so you can just put it in this formula that maximum bending stress is equal to maximum bending moment and c outer divided by I. So maximum bending moment is 2.25 kilonewton, so 2.25 into 10 to the power 3 will be newton into meter, and c outer is 0.04 divided by I, which is pi by 4 into 0.04 power 4 minus 0.025 power 4. So again, when you calculate it, you will get 52.8 into 10 to the power 6 Pascal. And when you convert it into megapascal, so maximum bending stress will be equal to 52.8 megapascal, which is the answer of this question. So maximum bending stress for the loading and the hollow circular shaft is calculated is 52.8. That was all about this problem 6-75. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-27. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by Rc Hibbeler. So statement is draw the shear and moment diagram for the beam. So you can see this is an overhanging beam and there is a triangular load of magnitude W0 at this end. At this end load is 0. There is a roller support at A, and at point B we have pin support. So you have to draw the shear and moment diagram for the beam. So let's start with the solution. So first step is that if you remove this roller support at point A, so you will be having reaction force offered by this support on this beam will be Ra, and if you remove this pin support, so there will be a vertical reaction force of Rb on this beam by this support. So first we will find this Ra and Rb by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So you can see one load is Ra, the second is Rb, and the third one is, if this triangular load is converted into a point load, so it will be equal to W1/2 into W0 into the length over which act, and this total length of the beam is equal to L. This is L because 2L/3 plus L/3 is equal to L, and that will act at a distance of L/3 from point B or from denser side. So this will be L/3. Now we apply this equation of equilibrium. So Ra into perpendicular distance is 2L/3. Let me show you. This is Ra, and about point B, this perpendicular distance is 2L/3, and this is producing clockwise, so it will be negative. So I will write minus the second moment that is produced due to this load, and perpendicular distance is L/3. Clear? And this is producing counterclockwise moment, so it will be positive. Here I have L as well because it is acting over length. So plus 1/2 this load, which is 1/2 W0 into L. W0 into L, and perpendicular distance is L/3 is equal to 0. So from here we will get minus 2 Ra L divided by 3 plus 1/6 W0 L square is equal to 0. So you will get 2 Ra L by 3 is equal to 1/6 W0 L square, and when you calculate, Ra will be equal to W0 L over 4. So this is the value of Ra. Now we'll find this Rb by using equation of equilibrium, that sum of all force along y direction must be equal to 0 and upward force is taken as positive. So Ra and Rb are upward, so Ra is W0 L by 4 minus this force, which is W1/2 W0 into L plus Rb is equal to 0. So if you take LCM, so this will be 4, so it will be W0 L minus 2 W0 into L plus Rb is equal to 0. So this will give you 4 minus W naught into L plus RB. So from here you will get this RB will be equal to W naught L over 4. Now you have RA and RB. So what we are going to do is that we will cut the beam at this and at this section. That this is section AA and this is section BB, and we will find the equation of shear and moment as a function of X. Clear? And then we will put the value of X to find the shear and moment, and then draw the shear force and bending moment diagram. So first step is that if you cut this beam over here, clear, and this, let this distance is X, this is section 1 and draw the free body diagram. So let me draw it first. Let this is the beam, clear, and you will be having a triangular load. Clear? This is the triangular load. This is the distance X where you cut this beam, and when you cut it, you will be having a shear force V, and you will be having moment M. This is your point 1. Clear? Now you can see that here the load is W naught. So if you take the ratio, we have two similar triangular. One is this one, and the other one is this one. So this is for the length of L, and this is for length of X. Clear? So by using similar triangles, if I take the ratio, this W naught over length L, W naught over length L will be equal to, here let the magnitude is W. So W divided by this distance X. So W divided by X. So where we will find W will be equal to W naught into X divided by L. So here the magnitude will be W is equal to W naught into X by L. Now when you convert this triangular load into point load or concentrated load, so it will be equal to 1 over 2 this load, which is W naught X over L, and the length over which act, and that length is X, and that will be acting at a distance of X by 3 from this point 1. Now we'll find this V and moment by using equation of equilibrium. So first equation of equilibrium is that sum of all force along y direction must be equal to 0 and upward force is taken as positive. And remember that section AA is for X is greater or equal to 0 and less or equal to L by 3. So X start from here is equal to 0, and at here you can see X is L by 3. So this equation will be valid for this region. Clear? Now V is downward, so minus V minus this load is downward. So minus 1 over 2 W naught X square over L is equal to 0. So from here you will get V is equal to minus W naught X square over 2L. Let this is your equation number 1. Now we'll find this moment by using equation of equilibrium, that sum of all moment about point 1 is equal to 0 and taking the counterclockwise moment as positive. So about point 1, the one moment is due to this, which is this load into perpendicular distance is X by 3, and this is producing counterclockwise moment, so it will be positive. And this external moment which we have taken as this will be positive. Now you can see that this load is producing counterclockwise moment, so in order to balance it, it will be in this direction. So let me correct it. This direction is this. So this minus moment which is clockwise plus 1 over 2 into W naught X square over L into perpendicular distance is X by 3 is equal to 0. So from here you will get this moment will be equal to W naught X cube over 6L. Clear? And this will be your equation number 2. So this equation 1 and, let me write it, equation 1 and 2 are valid for X is greater than or equal to 0 and less than L by 3. Now what we will do is that we will cut the beam at any region, that this is section 2 and this region is X is greater than or X is greater than L by 3 and less or equal to L. Clear? And we will draw the free body diagram. So let me draw it over here. So let this is the beam. Clear? There is a triangular load over here. Clear? This is the triangular load. At distance of L by 3 we have RA. So this is L by 3 and this is RA, and RA is W naught L over 4, and the total distance from this till the end of the beam is X, where we have cut this beam. So the remaining will be equal to X minus L by 3. And what about the magnitude over here? It will be the same, just like W naught X over L, because you can see you will have a two triangle, similar triangle. One is this one and the second one is this one. So W naught over L is equal to W over X, and this W will be equal to W naught X over L. Okay, W naught. So when you cut it, you will be having a shear force, clear, like this, and you will be having a moment that will be counterclockwise. Why? Because you can see now you have this force and this force as well. So we have taken it counterclockwise because its effect will give you a positive moment. Okay, so this is your point 2 because it is section at point 2. So when you convert this triangular load into a point load, so it will be equal to 1 over 2 this load, which is W naught X over L, clear, and it will act at a distance of x by 3, because x is the total length, it will be x by 3. Now we'll find this by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And remember that this is for section 2 and here x is greater than L by 3 and less or equal to L. Clear? So W naught L by 4, which is acting upward, clear, minus this load which is downward, minus W naught X over L, clear. So this load here you can see 1 over 2, this load into the length over which that is X. So it will be W naught X square minus W naught X square over L, clear. And the last thing is that minus V is equal to 0. So from here this V will be equal to minus it will be equal to W naught L by 4 minus W naught X square over L. Or you can say this V is equal to minus W naught X square over 2L. Here you can see you have 2 as well, so it will be minus 2, clear. So minus W naught X square over 2L plus W naught L by 4. This is your equation number 3. Now you'll find movement by using equation of equilibrium, that sum of all movement about point T is equal to 0 and taking the counterclockwise movement as positive. So about point 2, first movement is due to this W naught L by 4 and perpendicular distance is x minus L by 3. This is producing clockwise movement, so it will be negative. So I will write minus W naught L by 4 into perpendicular distance is x minus L by 3. The second movement will be due to this load and perpendicular distance is x by 3 and it is producing counterclockwise, so it will be positive. So I will write this load which is plus 1 W naught X square over L into perpendicular distance is x by 3 and there is external movement which is positive. Their sum must be equal to 0. So when you solve this, you will get this movement will be equal to minus W naught L over 4 into x minus L by 3 plus W naught X cube over 3L. Okay, just wait a minute. This is W naught X square over W naught X square over 2L. So this will become equal to 6L. Okay, now it's okay. This is your, this will be positive and will be equal to, this will be positive and this will become negative. Okay, so this is your equation number 4. Now we have equation 1, 2, 3, 4. This equation 3 and 4 are valid for x is greater than L by 3 and less or equal to L. Clear? Now we'll move to draw the shear force and bending moment diagram. For that I have to copy these equations. Let me copy these equations, some portions, so that we can move toward next page. I will copy it. I will move to second page and will paste here. Okay. So for shear force and bending moment diagram, I have to draw vertical lines from the end of this beam. You can see here, and there is a horizontal line to show the length in x, which is not known either in meter or in inches. So here we will draw the V. Now first, what we will do is that you have all these equations. So for x is equal to 0, put in equation number 1. Equation 1 is this one. So if you put x is equal to 0, so you will have V is equal to 0. Now for x is equal to L by 3, put in equation number 1. So what we will get if you put x replaced with L by 3, so you will get shear force will be equal to minus 1 over 8 W naught into L. You can put it and you will get this value. So this, can you correct it? This is V is minus 1 over 18 W naught into L. We can put it V is equal to minus W naught. You will replace L by 3 whole square over 2L. So that will be minus W naught L square over 18 L, which is equal to minus W naught L over 18. Clear? So I will again remove this. Now for x is equal to L. Clear? So put the value, put in equation number 3. So this is your equation number 3. So when you put x is equal to 3 in that, so what you will get is that you will get V is equal to minus W naught L over 4. Now you can see that at the end you will have RB, which is equal to W naught L over 4. It means that this will bring it to 0. So in between, let me plot it as well. So at x is equal to 0, we have first point is this one. At x is equal to L by 3, which is this one. Clear? So we have V is equal to minus 18. So let minus 18 W naught L minus W naught L over 18 minus W naught L over 18 is this one. Clear? And you can see you have RA as well over here. So which is W naught L over 4. So minus W naught L over 18 plus W naught L over 4 will bring it to 7 W naught L over 36. Okay, so you can see that this the shear force, the loading is triangular, so the shear force will be second degree curve and it will be like this. So let me join first these 2 points like this, like a curve. At this point you have plus 40, which will cause it to 7. So let 7 W naught L over 36 is this point. So shear force will change from this till this point. This is the point. Okay. Now at the end we have minus W naught L over 4, which let this is minus W naught L over 4, and at the end you have plus, which will cause it to come to 0. And you can see that this load is again linear load, so shear force will be a second degree curve and it will be like this. It will be like this. So we'll join these 2 points by using curve, not a straight line. I'm trying it to draw like a curve. Okay. Now here you can see the shear force is equal to 0. Clear? And we will find the location where this shear force acts, because at this location the bending moment will be the maximum. So you will find this value of x, which is not known. So what we will do is that put v is equal to 0 in equation number 3. So it will be equal to 0 will be equal to minus W naught x square over 2L plus W naught L over 4. So what we will get from here, that x will be equal to, let me check it. This will give you x square is equal to L square over 2, and x will be equal to 0.707 L. Clear? So this is x is equal to 0.707 L. So you can put this value of x in this equation number 3. So you will get v will be equal to 0. We will move toward bending moment diagram. So for bending moment diagram, I will again draw a horizontal line, and here x will be the length, and on y-axis we have moment. So what we will do is that for x is equal to 0, put in equation number 2. This is equation number 2. So if you put x is equal to 0, so moment will be equal to 0. So your first point will be this one. Here moment is 0. Okay. So for x is equal to L by 3, put in equation number 2. Equation number 2. So this is your equation number 2. You can see. So if you put x is equal to L by 3, so what we will get after the calculation, or after simplifying, you will get moment will be equal to 0.00617 W naught L square. I have already done it, but for reducing the length of the video, you can do it by yourself and you will get this value. Now you can see this is a positive value. Clear? This is a positive value. So while representing this positive value on moment diagram, it will cause the bending moment to go downward. So let this point is minus 0.00617 WL square. This is a convention given in the book. And you can see that this shear force is a second degree curve, and you can see the moment is 3 degree equation. So it will be just like, it will be also a third degree curve, and the bending moment will be like this, starting from 0 till this end. Okay. Now for x is equal to 0.707 L, put it in equation number 4. That will give you maximum bending moment. This is your equation number 4. So if you replace x with 0.707 L, so you will get the maximum moment, which will be equal to 0.0345 W naught L square. So we locate this point. Clear? And this will give you the point will be like. Welcome back. In this video, we are going to solve problem 6-193 that is taken from chapter number 6, bending, and book name is Mechanics of Material by Rc Hibbeler. So statement is draw the shear and moment diagram for the shaft if it is subjected to vertical loadings of belt, gear, and flywheel. The bearing at A and B exert only vertical reaction on the shaft. So you can see this is the shaft and this is bearing A and B that exert only vertical reaction. Clear? This is the gear where there is a 450 Newton load. There is a flywheel or belt. You can see this 300 Newton and there is a flywheel which have 150 Newton. So you have to draw the shear and moment diagram for the shaft. So let's start with the solution. So first step is that if you remove this bearing at A, so you will be having a reaction force. Let this is RA, and if you remove this bearing at point B, so you will be having a reaction force which will be equal to RB. This distance is 200 millimeter or 0.2 meter. This is 400 millimeter or 0.4 meter. This is 300 millimeter or 0.3. So we'll find this RA and RB by using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point A is equal to 0, and taking the counterclockwise moment as positive. So about point A, the first moment will be 450 into perpendicular distance is 0.2. When this is producing clockwise, so it will be negative. So I will write it minus 450 into perpendicular distance is 0.2 meter. The second moment about point A is this 300 Newton load and the perpendicular distance is 0.6 meter. And this is producing counterclockwise movement, so it will be positive. So plus 300 multiplied by 0.6 meter. The third moment will be due to this RB into perpendicular distance is now 0.9 meter. You can add them. This is 0.9. This is counterclockwise, so it will be positive. So I will write plus RB into 0.9 meter. And the last moment that is due to this 150 Newton load and now perpendicular distance is 1.1 meter, because when you add it, it will be 1.1 meter. Okay, so we will write this is producing clockwise movement, so it will be negative. So I will write minus 150 into 1.1 meter, and this will be equal to 0. So when you solve this from here, you will get this RB will be equal to 83.33 Newton. Now we will find this Ra by using equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So Ra is upward, so Ra, this 450 is downward, minus 450 plus this force is upward, so it will be positive, plus Rb, which is 83.33 Newton, and minus 150 is equal to 0. So when you solve this, you will get Ra will be equal to 217 Newton. Now you have Ra and Rb, so we will draw the shear force and bending moment diagram. So what we will do is that we will take two lines from the end of this beam. One is this one and other one is this one. There is a horizontal line to show the length that will be in meter, x in meter. On y-axis, you will be having a shear force having unit Newton. Okay, so we will take one division is equal to 50. So this is 50, this is 100, this is 150, this is 200. Similarly, minus 50, it will be minus 50, minus 100, minus 150, minus 200, and minus 250. So we'll first draw the shear force diagram. Now at this point, you can see you have Ra, which is 217. So we'll locate 217. Let this point is 217 Newton. So moving from point A till this load, there is no other shear force, so it will remain horizontal till this point. Okay. Now here we have minus 450 Newton that is acting downwards. So 217 minus 450 will cause it minus 233 Newton. So at this point, the load will be minus 233. So let 233 is this point minus 233. So your shear force will change from 217 to minus 233. And moving from this load till this mid, there is no other shear force, so it will remain same horizontal till this point there, and we will draw a horizontal line. Okay, now at this point you can see you have plus 300 upward, so minus 233 plus 300 will cause it to move to 66.7 Newton. So the load will be 66.7. So let 66.7 is this load, this point 66.7. You can choose your own scale as well. Okay, this is 67. Now moving from this mid till point B, there is no other shear force, so it will remain same horizontal till this point. So we will draw a horizontal line till this point. And again, you can see you have plus Rb. So 66.7 plus Rb is 83.33 will be equal to 150 Newton. So shear force will change to 150. So this will move to this point. This point is 150 Newton. And moving from 150 till end, there is no other shear force, so it will remain horizontal. And at the end, you can see 150 that is downward. So plus 150 minus 150 will bring it to 0. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for that, again, I will need the space. So let this is your horizontal line to show x in meter, and here you have moment. Let each division is 25. So this is 50. Similarly, minus 25 and minus 50. Okay. At point x is equal to 0, we have moment is equal to 0. So your first point will be this one. Now first area under the shear force diagram is this area, and you can see this area is, this height is 217 and this width is 0.2. So 217 multiplied by 0.2 is equal to 43.3 Newton into meter. So we'll look at 43.3. So let this is 43.3. This point is 43.3 Newton into meter. The unit is Newton into meter. And you can see shear force is a horizontal line with 0 degree, so bending moment will be 1 degree higher and slope will be increasing. So we'll join these 2 points using straight line. Now the second area under the shear force diagram is this area, and this area is equal to minus 233 multiplied by this 0.4, and this will be equal to minus 93.3. So plus 43.3 minus 93.3 will cause it to minus 50 at this length. So we'll plot minus 50 at this length. So minus 50 is this point. Okay. Now this shear force is a horizontal line with 0 degree and this area is negative. So bending moment will be 1 degree higher and slope will be decreasing. So we'll join these 2 points using a straight line. This is minus 50. Now moving further, the third area under the shear force diagram is this area, and this area is, you can see, height is 66.7 and this width is 0.3, and that will give you 20.01. So minus 50 plus 20.01 will cause it to minus 30. So at this length we will be having minus 30. So we'll plot minus 30. So let minus 30 is this point. This is minus 30. And you can see this shear force is a horizontal line with a positive area. So bending moment will be 1 degree higher and slope will be increasing. So we'll join these 2 points using a straight line. The last area under the shear force diagram is this area, and this area is 150 multiplied by this 0.2, which is equal to plus 30. So minus 30 plus 30 will be equal to 0 at this point, and we will get the bending moment like this. We will get a straight line and the slope will be increasing because the shear force area under the shear force is positive area, and this is a 0 degree line. So this is your bending moment diagram. And that was all about this problem 6-193. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-157. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by Rc Hibbeler. And the topic which we are covering is stress concentration. So statement is the step bar has a thickness of 15 millimeter. Determine the maximum moment that can be applied to its end if it is made up of material having allowable bending stress of 200 megapascal. So you can see this is the step rod. So here the thickness is 45, here thickness is 30, and here thickness is 10. And we have a fillet of 3 millimeter over here, fillet of 6 millimeter over here. So this is a step rod, and the moment M is applied on its end. So you have to find the maximum moment that can be applied. So let's start with the solution. So what we will get, you can see that we have 2 fillets over here. So there will be 2 stress concentration factors. So I will find them first. So stress concentration factor K for both these 2 fillets. So now for smaller section, let me show you the smaller section. For smaller section, you can see that this is the smaller section. Clear? So we'll find K for this smaller section. Clear? For that we will need W by H and R by H in order to calculate K. So here you can see that this is W. Clear? So W by H, W by H. So W here is 30 and H here is 10. So W by 10 will be it will give you 3. And what about by R by H? So you can see here fillet is 6 millimeter. So 6 divided by H is 10. So 6 by 10, and that will give you 0.6. So what we will do is that we will find this K, which is stress concentration factor. So you can see here this is 0.6. So you will take this vertical line, clear? And W by H is 3. So you can see this is the graph. So it is coinciding over here, clear? So if you move toward horizontal, so this K will be equal to 1.2. So I will write it here. K is equal to 1.2. Now we will find for larger section. Let me choose another color. For larger section, what will be W by H and R by H? So you can see here for larger section, this will be W, and that is 45. So I will write 45, and this will be your smaller section in 30. So 45 divided by 30 will give you 1.5. Similarly, R by H, here R is 3 millimeters. So 3 divided by H is 30, and that will give you 0.1. Now we will find this K value by using this table. So you can see this is 0.1. So if I draw a vertical line over here, so this is 0.1 and 1.5. So this is, you can see this is W 1.5, this graph. So if I proceed it, so this will be the point. And here you can see that if I remove this line, so you can see this graph will meet it at this point. So this will be your K, and that is 1.77. So I will write K value for this larger section, and that is 1.77. Now we will find allowable bending stress. We have been given allowable bending stress. So from here, we will calculate the moment. So we know that allowable bending stress is equal to K times M into C divided by I. Clear? So for smaller section, if you cut it, so you can see, you will draw the cross-sectional view will be like this. So this width thickness is given as 15 millimeter and this height is 10 millimeter. So thickness is 15 millimeter and height is 10 millimeter. This is 10 millimeter. So if you divide it in half, so this will be its neutral axis, and C is the distance from neutral axis till top or bottom. So this is C, and C will be equal to 10 divided by 2, which is equal to 5 millimeter. So C is 5 millimeter, which in meter is 0.005 meter. And what about I? So moment of inertia for this rectangular cross section will be 1 over 12 BH cube. So 1 over 12, B is 15 millimeter, which is 0.1015, and H is 10 millimeter, which is 0.00, which is 0.01 cube. And this is also, this will give you I. Now we have allowable bending stress, we have K, we have C, and we have M. So from here you can see that M will be equal to sigma allowable into I divided by K into C. So put the value. Allowable bending stress is 200 megapascal. So I will write 200 megapascal, 200 into 10 to the power 6, multiply by I, which is 1 over 12, 0.015, and H cube is 0.01 cube, divide by K. K for smaller section is 1.2. So 1.2 times C, and C is 0.005. When you calculate it, you will get movement will be equal to 41.7 Newton into meter. The unit will be Newton into meter. And this movement is for smaller section. Now we will move toward larger section. So for larger section, again, the moment equation is same, which is equal to sigma allowable into I divided by K into C. So you can see here that for larger section, it will be like this, the cross section. Since thickness remains same, which is 15 millimeter, but here you can see the height will be equal to 30 millimeter. Clear? So I will draw the cross section 30. This height is 30 millimeter, and this width is 15 millimeter. 15 millimeter. So if you take the half of this, this will be its neutral axis, and C will be this distance. This will be your C, and C will be equal to 30 divided by 2, which is equal to 15 millimeter, and C in meter is 0.015 meter. What about I? I is the moment of inertia. So for that, it will be equal to 1 over 12. Its breadth, which is 15 millimeter, and in meter it is 0.015, and height is 30 millimeter. So 30 is 0.030 cube. Clear? And K we have calculated for larger section is 1.77. Now you have all the values. Sigma allowable is 200 megapascal. So 200 into 10 to the power 6 multiplied by I is 1 over 12 to 0.015 multiplied by 0.01 cube divided by K, which is 1.77 multiplied by C. C is here is 0.0. C is 0.015. Now when you calculate all these values on right side, you will get movement will be equal to 254 Newton into meter. And this movement is for larger section. Now we have two movement. One is this one, and the second one is this one. So one is less than second movement. So largest movement that can be applied and will be safe is M is equal to 41.7 Newton. So this is the moment that we can apply on this system, so it will be safe. Now most of the students ask, since this value is the largest, so why we select this value? So answer is that if you take this moment, clear, and put in this formula. Let me show. If you take this moment and put it in this formula, so you will get allowable bending stress. You will get the stress, clear, which is less than allowable. So, and again, if you put this value for the largest section in this, so your stress will be less than the allowable for larger section. So it will be safe. What if we use this value in this equation? So your stress will greater than allowable, so it will fail. Hence we select this smallest value, and that will be the largest moment that can be applied on this system. And this was all about this problem 6-157. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 1-64. This problem is taken from chapter number 1, stress, and book name is Mechanics of Material by Rc Hibbeler. So statement is a vertical force of P 1500 is applied to the bell crank. Determine the average normal stress developed in 10 millimeter diameter of rod CD and average shear stress developed in 6 millimeter diameter pin B that is subjected to double shear. So you can see this is the bell crank which is applied a load of 1500 Newton, and this is the rod CD which is used to support this bell crank. and there is a pin support at point B. So this pin having diameter of 6 millimeter, while this rod CD has diameter of 10 millimeter. So you have to find the average normal stress in this CD, and there is a pin. You have to find the shearing stress in that pin. So let's start with the solution. So if you take the bell crank free body diagram FBD. So what if we remove this pin support at point B? So you will be having a vertical reaction force which is represented as By, and there will be a horizontal reaction force which is represented as Bx. Always try to draw it separately for saving time. I'm drawing it over here. And the rod CD exert a force FCD in this direction. You can see that this force is downward, causing the rod, causing it to move itward. As a result, the rod exert force in this direction, which is FCD. So we'll find this FCD, Bx, and By using equation of equilibrium. So first equation of equilibrium is that sum of all moments about point B is equal to 0, and taking the counterclockwise moment as positive. So about point B, first moment will be P into perpendicular distance is 450, and this is producing clockwise, so it will be negative. We will convert this 450 millimeter into meter, which is 0.45 meter. So P into 0.45, and I will also put the value of P, which is given as 1500. So 1500 into 0.45, and you can see that this FC is producing counterclockwise movement, because perpendicular distance is this one, and this is the force. About point B, it is producing counterclockwise movement, so it will be positive. So how we will get this vertical distance? So you can see if I draw perpendicular line, so this is 45, so this will be also 45, and this distance will be equal to, if you take sine of 45 degree, okay, let me explain it over here. You can see you have one, this FCD is 300 millimeters. So you can see you have one portion is this one, another one is this one. This is the perpendicular distance. So if you take sine of 45 degree, so it will be equal to, let this is y, it will be y divided by CB, which is 300 millimeter. So 300 millimeter, so y will be equal to, this is in millimeter, so y will be equal to 300 into sine of 45 degree, and the unit will be millimeter. So if you want to convert it into meter, it will be 0.30 sine of 45 degree. Now you can see this FCD and perpendicular distance is this one. Clear? This is the perpendicular distance, and it is producing counterclockwise movement, so it will be positive. So I can write plus FCD into 0.30 sine of 45 degree, and it will convert, the unit will be in meter. Okay, now their sum must be equal to 0. So from here you will get FCD is equal to 1500 multiplied by 0.45 divided by 0.30 sine of 45 degree, and that will give you 3181.98 Newton. Now we'll find Bx and By by using another equation of equilibrium, that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. Now you can see that we have one force Bx is in this direction, which is positive, and FCD is in opposite direction. Their sum must be equal to 0. So I can write Bx minus FCD is equal to 0. So Bx should be equal to FCD for equilibrium, and FCD is 3181.98 Newton. The last thing is that we can find the third force, which is vertical By, and it can be found by using this equation of equilibrium. So By minus this P, which is 1500, is equal to 0. So from here you will get By is equal to 1500 Newton. Now you have all three forces. So what we will go is that force in this rod is this one, FCD 3181. Clear? So what we are going to find, the average normal stress in rod CD, which is equal to force in rod CD divided by area of CD. So force in rod CD is 3181.98. Diameter of rod CD is given as 10 millimeter, which is equal to 0.01 meter. Clear? So we will use this, and diameter of it is equal to pi by 4 d square, and d is 0.01 square. So it is 3181.98, and diameter will comes out to be 78.54 into 10 to the power minus 6. Okay. Now if you further simply calculate it, so you will get average normal stress in rod CD comes out to be 40.5 into 10 to the power 6 Pascal, and you will get average normal stress in rod CD will be equal to 40.5 megapascal, which is the answer of our first part. Now we'll move towards second part, and in second part we have been asked to find the average shear stress in pin B. Okay, you can see here that this is By, and this is By, and this is Bx. So if you draw it by using head to tail rule, clear? So there will be a resultant force which will be B, and that will act on this pin B. Clear? So how we can find this? Because you can see one is vertical component by. Let me draw it. This is the B, this is by, and this is bx. Clear? So by using Pythagoras theorem, B will be equal to bx square plus by square under the root. So we will calculate this B by using Pythagoras theorem. So B is equal to bx square plus by square under the root. Put the value bx is 3181.98 square plus by is 1500 square under the root. So you will get this B will be equal to 3517.81 Newton. Now you have this B. So you can see if I draw this pin like this, if I want to draw the pin like this at B, so this B is acting over here. And it is given that it is double shear because there are two supports, so VB and VB. So this shear force will be equal to, this B will be equal to 2V, double shear. So shear force will be equal to B by 2. And 3517.81 divided by 2 will give you the shear force VB on the pin. And this shear force comes out to be 1758.91 Newton. Now you have shear force. We know that average shearing stress is equal to shear force divided by shear area, which is area of this pin B. So put the value 1758.91. The diameter of this pin is given as 6 millimeter, which is equal to 0.006 meter. So what will be the diameter? So diameter is pi by 4 d square. D is 0.006 square. And when you calculate it, it will give you 62.2 into 10 to the power 6 Pascal. And in term of megapascal, it will be 62.2 megapascal. And that is the answer of our second part. And this was all about this problem 1-64. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. I will suggest you to try this problem by your own, and if you feel any difficulty, you can ask. Thank you. Welcome back. Problem 1-81. This problem is taken from chapter number 1, that is stress, and book name is Mechanics of Material by Rc Hibbeler. So statement is the steel pipe is supported on circular base plate and concrete pedestal. If normal failure stress for the steel is 350 megapascal, determine the minimum thickness T of the pipe if it support the force of 500 kilonewton. Use a factor of safety against the failure is 1.5. Also find the minimum radius R of this base plate so that minimum factor of safety against the failure of concrete due to bearing is 2.5. The failure bearing stress for concrete is 25 megapascal. So you can see this is the pipe having axial load of 500 kilonewton. The outer radius is 100 millimeter and inner radius is not known, and thickness T is also not known. And this is the base plate that is mounted on this concrete base. Clear? So we have been given all the data. So you have to find this thickness T and minimum radius R of this base plate. So let's start with the solution. We can see we have steel plate and concrete. So we know that allowable normal stress for steel is equal to this load, which is acting as 500 P divided by the area of this pipe. Okay, clear? Area of steel pipe. And similarly, allowable stress, bearing stress for concrete is equal to this load P divided by the area of this concrete. So area of this concrete is similar to this area of this base plate. So area of concrete, you can see. Okay, now what we will do is that we will find this as area of steel. This is equal to P, and area of this pipe, hollow pipe, will be equal to pi by 4 or pi r outer square minus r inner square. Clear? And similarly here, this will give you allowable stress in steel, and allowable stress in concrete is equal to P divided by area of concrete. So which will be the same for this base plate. So it will be pi r square. Clear? So it will be pi r square. Now we will calculate this allowable stress in steel and allowable stress in concrete. So we know that for steel, first I will calculate for steel. So for steel, we know that factor of safety is equal to failure stress, clear, allowable stress in failure divided by allowable stress working. Allowable, what I have written, let me correct it. Failure stress in steel is equal to allowable stress in steel. So factor of safety for steel is given as 1.5. We are finding allowable stress. So allowable stress in steel, which is allowed and will be safe, will be equal to failure stress in steel divided by factor of safety. And that will be equal to 350 megapascal divided by 1.5. And this will give you 233.3 megapascal in steel. Clear? So I will write it. We get allowable normal stress in steel is equal to 233.3 megapascal. Now for concrete, we have also the same formula, which is that factor of safety is equal to failure stress in concrete divided by allowable stress in concrete. So from here, you will get allowable stress in concrete is equal to failure stress in concrete divided by factor of safety. So put the value, allowable stress is 25 in concrete and factor of safety is 2.45. So I will write 25 divided by 2.5 will give you 10 megapascal. Clear? Concrete. Now what we will do is that we have this value, we have this value, we have R naught. So we will calculate for steel. So let me choose another color. For steel, we know that allowable normal stress for steel is equal to P divided by pi into R naught square minus Ri square. So this is Ri square. This is 233.3. Allowable normal stress is 233.3 megapascal. So 10 to the power 6 is equal to P is given as 500 kilonewton. So I will write 500 into 10 to the power 3 divided by pi and R naught, which is 100 millimeter. So R naught is 100 millimeter and in meter it is 0.1 meter. And Ri is not known. So this is Ri. Clear? So 0.1 square minus Ri square. So from here you will get pi into 0.1 square minus Ri square is equal to 500 multiplied by 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6. And we will get pi into 0.1 square minus pi into Ri square is equal to 500 into 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6. So what we will get is that pi into 0.1 square minus this value 500 into 10 raised to the power 3 divided by 233.3 into 10 raised to the power 6 will be equal to pi Ri square. And if you divide Ri on pi on both sides, clear? So you will get 0.1 square minus 500 into 10 raised to the power 3 divided by pi into 233.3 into 10 raised to the power 6 will be equal to Ri square. And if you take under root on both sides, so Ri will be equal to 0.09653 meter. So in term of meter, it will be equal to millimeter, it will be 96.53 millimeter. Now you have Ri. So we know that Ri plus T is equal to R outer. Let me show you here. You can see Ri. This is Ri and this is T will equal to R naught. So you can put Ri is 96.53 plus thickness is not known and R naught is 100 millimeter. So thickness will be equal to 100 minus 96.53 millimeter. So from here you will get the thickness of this steel pipe is 3.47 millimeter. So this is the answer of our first part. Now we'll move towards second part, and in second part we have been find the radius of this base plate. Clear? So we know that we use this formula, and allowable concrete is 10 megapascal. So we know that allowable stress in concrete is equal to P divided by pi R square. So from here, this R square will be equal to P divided by pi into allowable stress for concrete. So put the value P is 500 kilonewton. So 500 into 10 to the power 3 divided by pi, and allowable stress is 10 megapascal. So 10 into 10 to the power 6 will be equal to R square. And when you take under root on both sides, square root on both sides, so you will get this as R will be equal to 0.1262 meter, or this R will be equal to, in millimeter it will be 126 millimeter. And that is the answer of our second part. So that was all about this problem 1-81. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. And I will request you to share these videos with your friends and help me in growing further. If you have any question, you can ask me in comment section. Thank you for watching.